Okay, so more two-dimensional dynamics. We're going to work in normal, tangential, binormal coordinates, and recall that the acceleration is given by v squared over rho inwards, where rho is the radius of curvature, and by v dot tangentially. The velocity is purely tangential. So let's proceed with a series of simple problems. We'll start with the Physics 12 problem. We have a pendulum cord swinging back and forth, and we want to find the cord tension at the bottom where the mass is moving at 3 meters per second. So we'll start with the force diagram. So we've got an inwards tension force and then an outwards weight, mg. Of course, the inwards direction is the normal direction. So when we write a force equation, the sum of the normal forces is T minus mg. That's got to equal the mass times the normal acceleration. But of course, the normal acceleration is v squared over rho. But in this case, we're moving in a circle, so the radius of curvature is the same as the radius of the circle. And so this is the applicable force equation. We want to find the cord tension. It's a 5 kilogram mass. It's moving at 3 meters per second. And the length of the cord is 4.2 meters, so that'll be the radius of the circle. So this expression here will give you the tension. Next, another circle problem. Here we've got a car driving in a corner, driving around a circular corner. Now, in top view, the inwards force will be the force of friction. It's actually a force of static friction because the car's tires are at rest when the tires are on the ground. Consequently, that's static friction. We're given here the coefficient of static friction. And there are two other forces in this case. We've got a normal force that's out of the page straight towards us, and then we've got a weight, mg, which is into the page, and they just balance each other. Now, the sum of the normal forces then, normal inwards direction, as opposed to normal perpendicular to the road, this n here, inwards towards the center of the circle, is just static friction, and that's got to equal the mass times the inwards acceleration. Static friction is mu s n, and then n in this case is the same as the weight. So mu s mg equals m v squared over rho, but of course we're moving in a circle, so the radius is the same as the radius of curvature. So we can cancel an m, and we want to find the maximum speed. So solving for v, we cross multiply the r. It's mu s rg, that'll be v squared, so we take a square root to get the speed v. Mu s is given as 0.75, r is given as 50 meters, and g is of course 9.81. So that will give us the maximum cornering speed. Now, let's imagine that instead of going at steady speed, that you're actually starting from rest and you're picking up speed. Okay. In this case, the force diagram is a little more complicated because you do have your inwards force here of friction that's going to keep you going in a circle. But in order to accelerate, you need a force from the road. Well, that force from the road is, again, a force of static friction. So there's going to be both a tangent component and a normal component of friction in this case. And the resultant friction will be the vector sum of those two. Now that resulting friction is still given by mu s n, which in this case is again mu s mg. So it's this that's restricted, this maximum thing here. So we need to write force equations for both the normal and tangential direction. Well, this is still going to be the same. There's the normal component of friction that's going to equal the mass times the inwards acceleration, which is v squared over r. Now, let's see, we're accelerating from rest at 1.25 meters per second squared, and that's constant. So v is going to equal 0 plus 1.25 t. Because the acceleration is constant, I can use constant acceleration kinematics. So there's an expression for v, and m and r are fixed. So I get for my normal component of friction, the mass over the radius times 1.25 t all squared. Let's consider the tangential dynamics. In the tangential direction perpendicular to the circle, we just have the tangential component of friction. That's got to equal the mass times the tangential acceleration. The tangential acceleration is the 1.25 meters per second squared of changing speed acceleration. So now we know the tangential and normal, so we can now write an expression for the total friction. It will just be the resultant of normal and tangential friction. But of course the maximum value that can be is the maximum coefficient times the weight. So this will equal mu s mg. So substituting in the normal component of friction, we see that it depends on speed, because as time goes on, your speed is going to increase. As a result, you're going to need more inwards friction to keep you going in the circle. Now we have to remember to square both of these. There we go. So there's the normal component squared, there's the tangential component squared, and all of that's going to equal mu s 0.75 times m times g. So all will be well until the time t given by this equation, because at that time static friction has reached its maximum value. If you go on increasing in speed, you will not have enough friction to keep you going in a circle, and you will slip. So there's a little bit of algebra here to solve for the time t, but there's the equation. Fairly straightforward. And that's what it looks like in the given space. Okay, let's continue on. Okay, it looks like it got pasted into the first page by mistake. Here is another assignment question for you with a swinging pendulum. You're going to write equations for the normal inwards direction and the tangential direction, and then solve those equations to find the tension in the cord, given that it started at 40 degrees and it swings down to 10 degrees. Now, the easiest way to find the speed is using an energy equation, and I'm giving you this as sort of a guide. You should work through this and try and make sure that it's very clear to you what's happened here. All right, here is the next problem. And in this one, we're not moving in a circle anymore. So we're moving along a quadratic, y equals x squared. So that means, of course, that we're going to have to determine what the radius of curvature is. So we're starting at rest up here at x equals 3, and then down here at x equals 1, we want to know what's the normal force, the slope and the normal force from that. The speed and the normal force from the slope. So let's consider the forces that act on this object. Obviously, there'll be a downwards force of gravity, and then in the normal inwards direction, you'll have the contact force from the slope, Fn. Now, we're going to want to resolve gravity into components. That means we need to know what this angle here is, theta. Once we've got that angle theta, then this looks a lot like ramp components. You're going to find the component of gravity that is going this way, outwards, because this is the inwards, this is the local radius of curvature, the local center of curvature rather. Normal force is towards that center of curvature, so that's in the n hat direction. This component of gravity is outwards. And you may recall that if this angle is theta, then this angle is as well. So we can write the normal force equation. The sum of the normal forces will equal the normal force minus mg, this component here is cos theta, and that's got to equal mv squared over rho. In the tangential direction, we have only the mg sine theta component that's pulling us down this hill, mg sine theta, and that equals the mass times the tangential acceleration of dv dt. So, as we've seen before, the velocity change with time is given by g sine theta. That's the tangential acceleration. So, there are the force equations. Now, we're asked to find the angle theta here. We'll use an idea from Cal 1. So this is, if we're sort of annotating this solution, there's the force equations. That's the first thing we were asked for. The next thing is the angle theta. The way we'll find that is the fact that y prime is the slope of a tangent line from Calculus 1, but the slope of the tangent line equals a rise over a run, where, say, this could be the rise and, say, this could be the run. If you look at that big triangle, rise over run, you see is tan theta. So you can find theta just doing the arctan of y prime. Now, y prime, given that y is x squared, y prime is 2x, and of course x equals 1, so theta will just be the arctan of 2, the angle whose tangent is 2. Now, if the tangent is 2, you could work this out exactly, but we're about to do sines and cosines of this angle, so this little triangle will be quite convenient for us. If the angle whose tangent is 2, that means 2 over 1, that means this side's 2 and this side's 1, and then just using Pythagoras, you could say, aha, that's got to be root 5. Again, you could work this out in degrees or radians, but for our purposes, we're not going to need it, because we just want to know what cos theta is, and now you can see in this triangle, cos theta is 1 over root 5. All right, next, the speed. Well, you can do that by integrating g sine theta all the way down the curve, or you could just use the energy solution, which is easier. So with the energy solution, you say you're starting at rest here at 3. So on your height, because the curve's y is x squared, that's a height of 9, and there's no kinetic energy there. Down here at 1, the height is x squared is 1. You're going to have a certain amount of kinetic energy, 1/2 mv squared, given by this equation. So that gives you the speed, 12.5 meters per second. Let's find the radius of curvature. Well, that is rho. Okay. And we know y is x squared, and you can go along filling this in here. Y prime is 2x, y double prime is 2. Now we are interested at x equals 1, this value is 2. Why do we need that? Because the radius of curvature is 1 plus y prime squared to the 3/2 over the magnitude of y double prime. So this is going to be 1 plus 2 squared. 2 squared is 4 plus 1 is 5. That's 5 to the 3/2. The half comes from the square root. And then we divide by y double prime, which is 2. So that's an expression for the radius of curvature. So we're pretty well ready to proceed here with calculating the normal force, because we know that in the normal direction, our force equation says normal force minus mg cos theta equals, this is supposed to be mv squared over rho. And we know rho, we know v, and we know theta. So we are in business. So let us come back over here and deal with this warning it's giving us. And then let's just jam this all in there, in case we need it for later. And now it's just substitution to find the normal force. So where are we there? So normal force minus, let's see, what was the mass of the skier? It is a 80 kilogram skier. Okay. So minus 80 g. Cos theta we could see in our triangle just ends up being 1 over root 5. Again, you could have just converted this to degrees and then just do the cos of whatever those degrees are. Equals 80 times v squared. V is 12.53 over the radius of curvature, and we've got the radius of curvature here, its exact value. This is 5 to the 3/2 divided by 2, so you end up with a factor of 2 here in the numerator. All right, now this is a very similar problem, and you could just work your way through the various steps, and it shouldn't be too much trouble. Okay, so we want to do dynamics in cylindrical coordinates. So we start with our coordinate system. Here is the r hat unit vector in the direction of increasing r. Here is the theta hat unit vector in the direction of increasing theta. Now, we're interested in the angle between the radial direction and the tangential direction. That's it right there. Let's do a little proof. So here's the particle at some initial time. There it is a little bit later. So there is a tiny change in r. That's a dr right there. From there to there. Here's a little bit of arc length. That's going to be, by the arc length formula, that's going to be r d theta. That's that little bit right there. So the dot is the angle that we're interested in, which is a capital psi. And see, if that's dot, then that's 90 minus dot, so this angle up here is also dot. Now that's true in the limit of infinitely small theta, because then this angle's 90 and this angle's 90. So if we come to our triangle here, then we've said that this is dr and this is r d theta. So for tan of psi, we get, okay, this is supposed to be r d theta. Good. So for tan of psi, we get opposite r d theta over adjacent dr. Since we usually know r in terms of theta, we write that as r over dr d theta. So that result there you can write in this box here. And it helps us find this angle, the radial tangential angle. Next up, our first example. Now we're going to take we're going to make this 5 kilograms, okay, because we want to just work with SI units. So a 5 kilogram ball is moving up a smooth vertical shaft due to this rotating arm. So the arm is pushing on it. Let's call that force normal arm right there. Now that's nicely in the theta hat direction. Okay, so the radial direction will be pointed this way, that's r hat, and then this direction right here, this will be the theta hat direction. And there's the normal arm force right here drawn with this blue arrow. Now, it's a vertical shaft, so we're also going to have a force of gravity. There's the force of gravity right there, that's mg. And then there's going to be a force from this groove, or this shaft, and let's call that the normal force from the shaft. Okay, now we want to write force equations for this. We're going to need to resolve gravity into components. We'll use this angle, which is also theta, and we see that that's a component in the negative theta direction, and that's a component in the negative r direction. This normal force from the shaft is partly in the negative theta direction and partly in the positive radial direction. Using alternate interior, we see that this angle up here is also theta. So we can come over here and we can write our force equations then. The sum of the forces in the radial direction. So we've got outwards normal shaft cos theta. Then we've got inwards mg sine theta. And that's going to equal the mass times the radial acceleration. The sum of the forces in the angular or theta direction, well, there's normal arm. Then you've got in the negative theta direction mg cos theta. Then you've got in the negative theta direction here normal shaft sine theta. And that's going to equal the mass times the theta acceleration. So the next thing we need to do is we need to do some kinematics. Well, if you notice here, this is the coordinate r, and then this side is fixed as 4. So we can draw a little triangle here. We could say, okay, that's r, that's theta, and this side here is 4, and then this is the vertical shaft. So we see secant theta is hypotenuse over adjacent. Solving that for r, we get 4 secant theta. So we can come over here to our chart and write 4 secant theta for the r coordinate. Now, for the theta, theta dot is given as 0.05 radians per second and constant, so theta double dot will just be 0. For our kinematics, we need to know r dot, which is the time derivative. So you do the time derivative of 4 secant theta, and the derivative of secant is secant tan, but then you need to multiply by d theta dt by the chain rule. D theta dt is a constant 0.05. 4 times 0.05 is 0.2. Next, for our double dot, we do the time derivative of that. Well, that's the time derivative of 0.2 secant tan. So we're going to have to use the product rule. So we'll keep the secant, differentiate tangent. Derivative of tan theta is secant squared times d theta dt. Then we'll keep the tangent and then take the derivative of secant. The derivative of secant is secant tan. And then, of course, at the end, we have the theta dot, the derivative of theta with respect to time. So we're going to get secant cubed times 0.2 times theta dot, okay? And that's going to be not 1. No, just 0.01, sorry. Secant cubed plus 0.01 secant tan squared. So then we're going to do our kinematics. R double dot, you know, is this minus r theta dot squared. You have r, you have theta dot. We have to substitute all of this. We are, however, going to work with an angle of 30 degrees. Okay? And what we get then for the radial acceleration, which is this first term here, when we substitute in our 30-degree angle, we should get a 0.00770. And then, when we substitute in for our theta acceleration, well, the theta double dot term just disappears because that's 0. Then it's just 2 r dot times theta dot. And that should end up being 0.0133. So now we substitute that into our force equations. Now they're recopied here. We need an extra factor of g there because we're working in imperial units. And then we need to solve for those two normal forces. So you know the radial acceleration, the angle theta is 30 degrees or pi over 6, and then those are the two accelerations. Let's try another dynamics problem in cylindrical coordinates. So here we've got a slider which is being again pushed by a rod through a groove. This time the groove is horizontal, so we're looking at it in top view, and we don't need to worry about gravitation. So let's consider again the force diagram. There's just going to be two normal forces acting on this object. There'll be a normal force from the track that's going to go in, seemingly, going to go inwards here. So that's normal force from the track. And then there's going to be another normal force from the arm pushing perpendicular to the arm. And that's going to be about like, about like that. So that's normal arm. Now in our coordinate system, this is in the theta hat direction, okay? And then this is the radial direction, r hat, just parallel to this arm here. Now the direction it's moving is the tangent direction. So this angle right here, dot, that's psi. So this will be 90 minus dot. So this is dot over here. And then probably most telling, this angle up here is also psi. So that's helpful because we can use it to get the components of this normal track force. We see that it's partly in the negative radial direction and partly in the positive theta direction. So let's write then our force equations. So we're going to have the sum of the radial forces. So we've only got one. It's in the negative radial direction, and it's normal track, and that's going to be the opposite side. So that's sine of that psi angle. And then the sum of the angular forces, we've got normal, arm, then we've got this positive theta component, normal, track, cos of psi. Okay. Now, we need to know what that psi angle is, don't we? Well, we know that the shape of the track is 1 plus 2 theta. And we know that tan of psi is r over dr d theta. So this is 1 plus 2 theta. Dr d theta is just 2. Okay? Now, we're going to work at an angle theta of pi over 4. So if you put in pi over 4 here, and then do the inverse tangent and solve for the psi angle, I get 0.9096 rads. Okay? So now it's time to do our kinematics. So we know that the r is 1 plus 2 theta. So ddt of that is just going to be 2 times the ddt of theta, which is just 2 theta dot. And we're told in the problem that theta dot is a constant, 0.2, and doesn't change. So 2 times theta dot is just 0.4, and that never changes. So r double dot is 0, and theta double dot is also 0. So we go ahead to do our kinematics then. This is the radial acceleration, AR. This is 0 minus our value of r. Now we've got to put in our angle, which is pi over 4. So this is 1 plus pi over 2, which is 2.57 or so. The pi over 2 comes from twice the pi over 4 angle that we're working with. And then you multiply that by theta dot squared. And that works out to be, let's just pause here for a moment. Okay, so when you put in that negative 2.57 times 0.2 squared, you get, okay, come on now, I'm back here. You get a radial acceleration of minus 0.103, and then this term is 0 for the theta acceleration, and it's 2 times 0.4 times 0.2. You get a theta acceleration of positive 0.16. Alright, so then we substitute those two accelerations and the value of psi into our force equations, and we solve for the two normal forces.